Hello everyone, I'm Norman Wildberger. Today we're going to initiate a new direction for our Explorer Research Level Mathematics series. This is a very important one, which will also be really extensive and I think full of interesting developments that you can participate in by becoming a member of the Wild Egg Maths YouTube channel or by accessing the videos through my Patreon page. So it's called Algebraic Calculus and the Geometry of DCB Curves. That's the topic that we're going to be pursuing, and I'm going to try to explain aspects of the algebraic calculus to you in the direction of the geometry of these remarkable curves called de Castelnau-Bézier curves, which from my point of view are the central objects in calculus. Now, there's an algebraic calculus course, and I hope that a lot of you will be motivated to take that course. That is the reference for this entire discussion, and it's also supported by the algebraic calculus lectures on the Wild Egg Maths YouTube site. But this series here is going to be more informal and more exploratory. So we're going to be less interested in establishing solid foundations and rather interested in exploring things and going through doors, opening new investigations for you to actually participate in. So I want to get you involved in thinking about research level mathematics, which is interesting. So along the way, of course, I'll have to tell you a little bit about algebraic calculus. So I'm not going to assume that you know about the algebraic calculus. You will learn a little bit about it, but don't expect that you're going to get a complete view from this, all right? You're going to get an overview and some insights, but for the full story, which is by now very extensive, you want to go to the Open Learning course on algebraic calculus or start watching the videos. So what's the basic point of the algebraic calculus? So it's a new approach to calculus, which is really dramatically different from all the other textbooks and courses that you're going to find. In the algebraic calculus, we're interested in doing everything algebraically. We're wanting to avoid anything that involves infinite processes or the assumption that we can do an infinite number of things, including the usual way of approaching limits and real numbers. Now, many of you will think that this is an essential aspect of calculus, but you will see that it's not, okay? It's not essential, that we can do everything algebraically, and that means that we can end up specifying everything completely on the page. That's what we want to do. That connects naturally with what computers can do. So everything that we're doing in this approach, we can get support from the computational side of things directly, okay? Now, what about these curves? So from my point of view, the central objects in calculus are not functions, they are rather curves, and they're higher dimensional extensions, surfaces, and so on. And in the planar situation, the heart of the matter are these particular kinds of curves, which are polynomially parametrized curves, also known as de Castelnau-Bézier curves. Now, remarkably, these things really only came into clearer focus in the 1960s with the work of Paul de Castelnau and Pierre Bézier, two brilliant French car engineers who really transformed this entire area of algebraic geometry. And for us, these objects are actually not just important in algebraic geometry and the theory of curves, but they're actually the central objects in calculus. Okay, so what is a de Castelnau-Bézier curve? Well, here's a picture, okay? You see you've got, in this case, 5 control points, P0, P1, P2, P3, P4. And the corresponding curve is this in light blue, okay? It turns out to be a quartic curve. It's a curve that when you write it out in coordinates involves degree 4 polynomials. Or I prefer to call them polynumbers, and we'll talk about what that means. And this diagram sort of exhibits what's happening. So what's happening here is that there's a parameter, t, which runs from 0 to 1. And as this parameter runs from 0 to 1, you have these sort of secondary points, the Q's, Q0, Q1, Q2, moving between the various P points. So Q0 runs from P0 to P1, Q1 runs from P1, P2, etc. And these all sort of move proportionally. So if T is, say, 1/3, then Q0 will be 1/3 of the way along. So actually, in this case here, T happens to be 0.4, and this Q0 is 0.4 of the way along. Q1 is 0.4 of the way along here, Q2 is 0.4 of the way along here, and Q3 is 0.4 of the way along here. Now, once we have the Q's, then the next level, we create the R points, which have the same relation to the Q points as the Q points did to the P points. Okay, so R0 is 0.4 of the way along between Q0 and Q1. R1 is 0.4 of the way between Q1 and Q2, and R2 is 0.4 of the way between Q2 and Q3. Once we have the R points, then we similarly create the S points, which are correspondingly 0.4 along between R0 and R1 and between R1 and R2. And then finally, in this example here, the last point is this T0, which is 0.4 of the way between S0 and S1. Now, as this parameter T varies from 0 to 1, all of these points are going to move except for the fixed control points, P0 to P4. And the locus of this point T0, which is the most complicated of all these points, the locus of that will be this curve here, which is then the de Castelnau-Bezier curve with control points P0, P1, P2, P3, P4. And I'm claiming that these things, okay, these curves are actually properly the central objects in calculus, sort of at the most elementary level. They're at the heart of things. So now it turns out that these curves are not only critical for calculus, but they have their own intrinsic geometry. And it's the geometry of these DCB curves which interacts in a beautiful way with the algebra, or maybe the analysis of the curves themselves. So you see that there's a kind of a discrete aspect because the entire curve is controlled by these 5 control points. It's a very discrete thing. Okay, great. So I want to solidify this initial understanding. So people who will have taken algebraic calculus will have a lot of experience with these things because these are central things in the course. But if you've taken a standard calculus course, you likely will not have seen very much of these things, and they certainly will not be playing a central role. Because that's a big change that you have to make. You have to adjust yourself to thinking about these curves as being really at the heart of calculus. Okay, so here is GeoGebra, and here's a worksheet that illustrates what I've been talking about. And the beauty of GeoGebra is that we can see these things in action and really get an explicit sense of what's going on. So the control points, the P0, P1 up to P4 points, they are movable, all right? They are movable. And here is a slider which represents this, this variable t running from 0 up to 1. So let's have a look at what happens as t sort of marches forward. Here t is increasing, and you can see Q's, the Q points, traversing their corresponding segments. Okay, maybe I'll animate it on so you can sort of see it. Okay, so the Q points are moving proportionally, and while they're doing it, now we're going backwards, the R points are going between the Q points, and as that's happening, the S points are going between the R points. Okay, and this point T0, which is actually tracing the curve, is going between the S points. You can see that's the point actually that's generating the curve. Okay, that's a de Castelnau-Bezier curve, sometimes in the literature called Bezier curves, but we are going to call them de Castelnau-Bezier curves because Paul de Castelnau had just as much of a role in their development as did Pierre Bezier. Now, let's stop this animation. And I want to show you some other points. So I'm going to turn off this locus here and look at a simpler thing. So suppose that we just look at a simpler lower dimensional or lower degree situation where we only have two control points, P0 and P1. Okay, well, in that case, there's only this one intermediate point Q0, and it's kind of obvious what Q0 is doing. Q0 is moving from P0 to P1. And what is actually the equation for Q0? Here's Q0. So how is it generated? So let's have a look at what the formula for it is. So here's the formula, that Q0 is 1 minus T times P0 plus T times P1. So it's a linear combination of these 2 points. In fact, more properly, it's an affine combination. Okay, the sum of these coefficients, 1 minus T and T, sum to 1. T is between 0 and 1. Both of these coefficients are going to be positive, that is greater than or equal to 0, and between 0 and 1, in fact. So it's sort of the weighting is starting with a complete weighting at P0, and then as T ranges up, the weighting goes more and more towards P1, and we're just traversing this linear segment from P0 to P1. Fine. And now let's look at the next level up. When we have P0, P1, and P2, we have 3 control points. Okay. Now we have Q0 and Q1 traversing these 2 segments, and now we have this next level point, R0. And now we're going to show you what R0 does. Okay, so R0, this point here, as T ranges, is going to traverse this green path. The green path starts from P0 and goes to P2, but it's no longer a line. It's actually a quadratic curve, which in fact is part of a parabola. Okay, and of course we can move this around. We can move these things around. So maybe this looks more like a parabola, something like this, right? Recognize that looks like a parabola, and it is. Okay, and it's given by the same kind of formula that R0 is an affine combination of Q0 and Q1, and Q0 and Q1 are themselves affine or convex combinations of P0, P1, and P2. Okay, let's turn that locus off and go up one more step. Okay, so now let's look at 4 control points, P0, P1, P2, and P3. So now we have Q0 involved, Q1 involved, and also Q2 involved. And now we have both R0 and R1 also traversing these 2 segments. And once we have them, then we can look at this next level point, the S0, which is traversing the segment between R0 and R1. And let's have a look at the locus of S0. Here it is here. Okay, so let's just traverse this around. So as this is going around, you can see that S0 is traversing. And notice also that this segment between R0 and R1 that S0 is traveling on is tangent. It's always tangent to this curve. Now this is not a parabola. It doesn't really look like a parabola, does it? It's not a parabola. In fact, it's a part of a cubic curve. It's a cubic curve. And since we have 4 control points, we can change the nature of this thing quite pleasantly. We can move it around. We can even do something like this. You see what's happening there? This is looping around like this. Definitely not a conic. This is a cubic kind of behavior. This is actually a node here. Right? This curve is crossing itself. Okay, so that's a cubic curve. So these 2 kinds of curves, the quadratic and the cubic DCB curves, are especially important in applications. And the reason is evident from the geometry here. And that's that these initial segments, the initial segment here and the sort of final segment here emanating from the endpoints, are in fact tangent to the curve at the endpoints. So this segment here is dictating the direction, the initial direction of the curve, and this segment here is dictating the final direction. So if we fixed P0 and P3 and just moved P2 and P1 around, then of course the endpoints are staying fixed, and we can sort of change the direction in which the curve is emanating from those endpoints. Now, this control over the endpoints means that these curves are ideally suited to pasting them together. So if you have some complicated curve, like maybe an outline of a part of a car, which would have been what Bézier and de Castelnau were interested in, then what you can do is you can take that complicated curve and sort of slice it up, subdivide it into more simple pieces. And these simple pieces can then be approximated by quadratic or cubic curves. And if we put the control points in the right positions, we can guarantee that these different curves that we're introducing meet smoothly, or at least pleasantly, at their common endpoints. So it means you can line up their tangents so that it has the appearance of being rather smooth. Okay, so that makes these quadratic and cubic de Castelnau Bézier curves especially important in design and industrial applications, and that's why they have been so extensively used in the last 50, 60 years. All right, great. So now let's just go up to our final thing. So we've just been talking about the locus of S0. Let's turn that off and return now to one higher dimension where we look at all 5 control points. So now we also have an R2, R0, R1, R2. We have an S0 and now an S1 as well. And then correspondingly between S0 and S1, we have this T0, which we've already seen. And if we turn the locus of that on, then we get that quartic DCB curve. So DCB is just a short form for de Castelnau-Bézier. And we can move these things around. And with a quartic curve, you have more flexibility than you do with the cubic. But on the other hand, it is more complicated algebraically. So actually in industrial applications, the quadratic and the cubic ones are used principally. But from a theoretical point of view, these higher degree DCB curves are also very interesting. And they have a really central theoretical role in the algebraic calculus. All right, great. So now let's introduce a little bit of algebra and notation that allow us to access this very rich mathematical subject. So this is all happening in what's usually called the world of polynomials, but for us, we want to use variants of those called polynumbers. Okay, what is a polynumber? A polynumber is a list of numbers written vertically in something like square brackets. So in scientific workplace, I'm going to use these square brackets to denote polynumbers. So you see a vertical vector in square brackets, chances are it's a polynumber. So this particular one has 4 entries, and we'll typically start the labeling from the top with a 0 index. So this is the entry or coefficient P0, and then P1, P2, and P3. And let's say, to be specific, that we're talking about this particular polynumber, 1, 2, 0, minus 3. Now, we're going to, however, agree that adding or removing zeros to the bottom of this square vector does not change the polynumber. So this polynumber that we've just been talking about is equal to this one here, which is exactly the same, except that it has an additional 0 below the minus 3. And in fact, we could add any number of zeros. So for example, I could add another 0 there, and it would still be equal. Okay, so this is not exactly a vector. I don't want you to think about these things as exactly vectors. They are a little bit like vectors, but they have this sort of extendable aspect. Now, the degree of a polynumber, like in general, coefficients P0 to Pk, is k if this last entry is non-zero. So the degree is determined by the last non-zero entry as we read down. And there's a special polynumber, the 0 polynumber, which just has a single 0 in the top 0th place, and that we'll say that its degree is not defined. Okay, so now we can introduce some algebraic operations on these polynumbers. So the usual linear structure is determined component-wise. So multiplying a polynumber by a scalar, in other words, a number, is just the usual component-wise multiplication. So 2 times the polynumber 7, 3 will be the polynumber 14, 6. And when we want to add or subtract polynumbers, we're going to use this flexibility in adding zeros at the bottom. So the degrees of the polynumbers don't need to match in order for addition or subtraction to happen. So that's different from the world of vectors that you might be used to. Okay, so in an ordinary vector world, you're not allowed to add this vector with 2 components to this vector with 3 components. However, in this context, this is regarded as a polynumber and it's extendable. So we can just add a 0 and it hasn't changed. Now we have the same number of elements and the addition is just component-wise. So 7 plus minus 4 is 3, 3 plus 2 is 5, 0 plus 8 is 8. Okay, but we don't actually need that 0. We could just write it like this. And same thing with subtraction. Now, the interesting operation is the multiplication. Okay, the multiplication is determined by what's called the Cauchy product of lists. And okay, if you've watched my videos, you'll know all about this, but in case you haven't, the Cauchy product is determined as follows. Let me illustrate it in this example here. So we're multiplying the polynumber 1, 3 with the polynumber 5, 2. The 0th entry here is the product of 1 times 5. The 1 entry is the product of the 0 entry here and the 1 entry here, so 1 times 2, plus the product of the 1 entry here and the 0 entry here, so plus 15. For a total of 17. And the 2 entry is obtained by the product of the 1 entry and the 1 entry, which is 6. Now, the unit polynumber, which is another sort of important basic polynumber, is just the polynumber with a single 1 up at the top, and we'll maybe denote it with a bold 1 in correspondence with our bold 0 for the 0 polynumber. So these are pretty close to each other. And this is the unit in this multiplication, so that if you multiply any polynumber with this one, you're going to get the other polynumber. Now, here we come to the really interesting sort of novel aspect of this story, is that there's a third polynumber which is really important. So we have 0, we have 1, and we have alpha. What is alpha? Alpha is this particular polynumber. Okay, it's a polynumber with a 0 up at the top and the next entry is 1. Arguably, it's sort of the next simplest polynumber. And it's not hard to see that powers of this thing will consist of columns or vectors of zeros followed by 1. So if we compute alpha squared, exactly in this fashion, we're going to get the polynumber 0, 0, 1. And if we compute alpha cubed, we're going to get 0, 0, 0, 1. Okay. Now, the important thing to note here is that this alpha that we're introducing is not a variable. For me, the notion of a variable is problematic. I don't really know how to define that exactly correctly. So here, the alpha is just a polynumber. It's this particular polynumber. Okay, but it's very convenient because powers of alpha then form a natural basis, or you could say that alpha is a generator for this algebra, let's call it Paul, of polynumbers, in the sense that every polynumber is then a unique linear combination of powers of alpha. So for example, this P that we talked about earlier, which is where, this P right here, okay, there it is again. I'll just grab that. If we look at this P, let me put it here. So this poly number P, which is 1, 2, 0, minus 3, can be written as 1 plus 2 alpha plus 0 alpha squared, so we don't include that, minus 3 alpha cubed. And this product up here that we've computed with the Cauchy product amounts to 1 plus 3 alpha times 5 plus 2 alpha equals 5 plus 17 alpha plus 6 alpha squared, which happily is the usual way of multiplying polynomials. So this Cauchy product is just sort of the list encoding of the usual familiar polynomial multiplication. We're sort of starting from that point of view, okay, but it's equivalent. Okay, so from this point of view, a poly number like p doesn't have to have a variable behind it. We do not have to say p is equal to p of alpha. P is just this list, okay? But we are able to evaluate it also. So we agree that, let's say we want to evaluate this p at 2. Then what we do is we take the alpha form of it, so that's like the polynomial form of it, and just replace the alpha with the 2. So p of 2 will be 1 plus 2 times 2, which is 4, minus 3 times 2 cubed, is minus 24. So that'd be minus 19. Okay, and so that's a quick introduction to polynumbers, which are more or less polynomials, but maybe in a slightly more rigorous or careful way, maybe a computer science kind of approach. It's sort of data theoretic. What's the essential of a polynomial? The essential is the list of coefficients. Okay, so now we come to the critical object, which is a polynomially parametrized curve. What does this mean? So we have two polynumbers, p, say of degree down to k, and q, say degree down to l. Then we can put them into a list, gamma. So gamma is this list. It's a list, p comma q. It's a list of two polynumbers. And that's what a polynomially parametrized curve is. Okay, so a curve for us in this context is just a list of two polynumbers. So note that a curve is not a set of points. It's a completely finite specifiable object. Okay, to encode such a thing on a computer, you would have to create a list with two objects, and each one of these objects would be one of these polynumbers which we've already defined. So that's a polynomially parametrized curve, and it could be quite general because we're allowing quite general polynumbers or polynomials, effectively the same, for these p's and q's. Right, great. So now what about the Castelnau-Bézier curves? Okay, so we want to connect what we've just talked about with this sort of geometrical situation where we start with control points and somehow create this curve from a locus of combinations. So it turns out that these things are crucially connected, and it's really important to understand this, okay? So we're now going to explain why these polynomially parametrized curves that we've just introduced turn out to be exactly the same as the de Castelnau-Bézier curves, or DCB curves for short. Okay, so usually these DCB curves are defined sort of separately. That is, usually we start with the linear case, and then the quadratic case, and then the cubic case, etc. And that's still how I want you to think about things, that we have an order of complexity. But I want to sort of put them all in the same kind of pattern, agreeing that these things are going up in complexity. But I want you to think about the whole thing somehow as a consistent pattern. Okay, so to do that, let's consider a sequence of control points, P0, P1, P2, etc. Okay, so these are planar affine points. And these are going up to some specific but unknown point. So this is a sequence that carries on in some fashion, but maybe it carries on beyond our current window of computation or visibility. Okay, but we're not going to claim that we're going to be looking at an entire sequence going to infinity or any such thing, okay? Because we are not allowed to do an infinite number of things, including looking at an infinite number of elements in a sequence. But I do want to give you this ongoing orientation right off the bat, that we're thinking about building things up sort of one stage at a time. So what we want to do is we sort of want to control what's happening at the kth stage, and how the kth stage relates to the k plus first stage. Okay, so we need to introduce some coordinates. So let's suppose these points have coordinates as follows. So the 0th point has coordinates p01, comma P0, 2. So the 0 is the index, and 1, 2 represents the first coordinate and the second coordinate, like the x and the y, if you like. Okay, the point P1 has coordinates P11 and P12. P2 has coordinates P21 and P22, etc. Okay, so remember what we did in the GeoGebra app is we introduced from the P points the Q points. Okay, and here's the formula that we used. That Q0 was this affine combination of P0 and P1, depending on a parameter T. So we're thinking about a parameter T. For now, you can think of T as being a number between 0 and 1. So there's Q0, and correspondingly, Q1 is just what you get when you bump up all the indices by 1. Q2 is what you get when you bump up all the indices by another 1, etc. So now, the locus of Q0, if we just concentrate on Q0 and ignore the other ones, the locus of Q0 as T varies is a linear DCB curve. Okay, that's the line segment going from P0 to P1 that I showed you initially. Okay, so that's a DCB curve. That's sort of the simplest kind, except unless you just have a single point. And so this is a line or a line segment passing through P0 and P1 when T equals 0 and T equals 1 respectively. But a degenerate situation is possible because we are allowed to have P0 and P1 equal, in which case all of these Q0s Q0 will just be P0 itself. Okay, and now we want to go to the next stage. Okay, the next stage, we're going from the Q points to the R points, and we're doing that in exactly the same way as we went from the P points to the Q points. Okay, so this is sort of just the algebraic version of what I showed you geometrically with the GeoGebra app. So R0 is a combination of Q0 and Q1, and again, the coefficients depend on T in exactly the same predictable pattern that we've seen already. 1 minus TQ0 plus TQ1. Correspondingly, R1 is a combination of Q1 and Q2. R2 is a similar combination of Q2 and Q3, and so on. So, we could go up to 100 or however many control points we had. If we had 100 control points, say P0 up to P99, then these the Qs would only go up to 98. Okay, and then the R's would only go up to 97. So the number of each of these additional points that we're creating, it reduces by 1 each time, just as we saw in the app. Okay, so now let's concentrate on this R0. Well, the locus of R0 as T varies is a quadratic DCB curve with control points P0, P1, and P2. See, R0 depends on Q0 and Q1, and Q0 depends on P0 and P1, while Q1 depends on P1 and P2. So altogether, this R0 depends on P0, P1, and P2, but none of the other Ps. Okay, and then we can keep going. Once we have the R points, then we can get the S points formed exactly the same way. Okay, combinations of the R points that we've just obtained. And then the locus of S0 as T varies is a cubic DCB curve. Now with control points P0, P1, P2, P3, because those are the control points that figure in the expression for S sub 0. So one can continue in this fashion. You can create quartic DCB curves from 5 control points, then quintic DCB curves from 6 control points, and so on. Now, let's have a look at sort of what these things look like more explicitly. Okay, so let's go back to the Q0. The Q0 was a combination of P0 and P1, and we can sort of rewrite that. Here it is in terms of P0 and P1, but we could write it rather as a polynomial in T. Okay, so the things not involving T are P0. The things involving T are this term P1 minus P0. When we look at it this way, we see that what we're seeing is that Q0 is when you start with the point P0, and then you go a certain multiple of this vector. This P1 minus P0 is really a vector from P0 to P1. And this is describing the motion of starting with P0 and adding a multiple of this vector. So clearly you're starting at P0 and ending up at P1 when t is equal to 1. So we necessarily get a polynomially parameterized curve, because when you think about substituting the coordinates of these points, okay, then you're going to get an expression like this. So this Q0 is going to have an expression in t, which is going to be linear in t, because the t is only occurring to degree 1 here. So there's going to be a linear expression in the first coordinate and another linear expression in the second coordinate. And let's give some names to those coefficients. So let's say that this linear expression is C01 plus C11t. Okay, so the second entry here is telling us telling us which coordinate we're in. So here we're in coordinate 1, and here's coordinate 2. Okay, and the 0 is sort of like degree 0 stuff, and the 1 is referring to the degree 1 stuff. Okay, now if we compare coefficients, so we can write this locus of Q0 in terms of polynomials like this, but we can also go back up to what Q0. Here's Q0 here in terms of P0 and P1, or I guess it's the same right here. There's Q0 expressed in terms of P0 and P1. And we know what P0 and P1 were. Let me remind you of that. Here are P0 and P1. Okay, so we could write Q0 also in terms of these guys. What does that look like? Well, we end up getting this expression, this relation between the C coordinates and the P coordinates. Okay, this is a matrix equation, so a little bit of linear algebra here, all right? So what this is saying is that the C01 and the C11, okay, this first column, that's obtained by taking the first column here, the P01, P11, and applying this thing here. So what does that matrix multiplication do? Well, it gives you C0 is equal to P01, right? Plus a 0, okay? And then the C11 is going to be minus P01 plus P11. So if you think about it, that's exactly what you're getting from this expression here. So this is then an algebraic relation between the coordinates of the control points, and the entries of the polynumbers or the polynomials in the locus that we're finding. And to go back and forth from one of these to the other involves multiplying by this 2 by 2 matrix. Or to invert, we have to multiply by the inverse of this matrix. Now, what is the inverse of this matrix? Let me just calculate that for you. I hope you can calculate this kind of thing, but okay, so let's put a -1 here, equals. So the inverse of this matrix is this matrix here. So if we wanted to express the P's in terms of the C's, we would write this P matrix is equal to this matrix on the left times this C matrix on the right. Okay, now let's look at the quadratic case. So we're going to do the same thing, but one step up. So in the quadratic case, R0 was 1 minus TQ0 plus TQ1. So now it gets a bit more involved because the Q's themselves were linear combination of the P's. So here's the expression for Q0. We have to multiply that by 1 minus T. And here's the expression for Q1. We have to multiply that by T. When we expand all of this, we get this expression in terms of P0, P1, and P2. We get a combination of these 3 points with coefficients 1 minus T all squared, 2 times 1 minus T times T, and T squared. And if we want to, we can rewrite this in a similar way as we rewrote this, as an expression in powers of T. So the constant term will be P0, which only appears here, plus 2T times P1 minus P0, plus T squared times P0 minus 2P1 plus P2. What's this telling us? This is telling us that we're obtaining a polynomially parameterized curve of degree 2. In other words, in terms of the dependence on the parameter t, okay, this is a purely quadratic dependence. In other words, the locus of R0 as a function of t will have this form. It'll be similar to what we had in the previous case, except that we have to go 1 degree higher. We have to introduce a plus c sub 2 1 t squared and plus c 2 2 t squared. Now you can replace the p0 and the p0, p1, and p2 with their coordinates. All right, so here are the coordinates of p0. That first row is really p0. This second row is really p1. This third row is really p2. And so you stare at this, and I want you to make sure that you do this and go through it to convince yourself, all right? That you convince yourself that this, what's happening here is allowing us to go from the p coordinates of the points, capital P0, P1, P2, to these coefficients of these quadratic polynomials that are appearing here. And the form of what we're getting here is essentially encoded by this linear algebra equation, relating the over here we have in the first row we have the linear terms here, the constant terms. Then the second row is the linear terms, C11, C12, and the third row are the quadratic terms, and given by this 3x3 matrix. Cool. So some linear algebra is happening here. So let's take the inverse, and one of the common things to do. Okay, so we get some matrix that looks like this. In particular, this thing is invertible. So if we wanted to, we can invert this. If we know the p's, we can get the c's from this equation. But if we know the c's, we can get the p's by multiplying the C matrix with this inverse matrix. Okay, great. Okay, now similarly for the cubic case, I won't go through it, but you can check the same kind of story is happening. Okay, please check this. Check this. Okay, cubic case is especially important, so I really want you to make sure, go through the algebra, get used to doing some arithmetic with polynomials involving t, and convince yourself that this S0 point, which is a combination of R0 and R1, can be expressed in terms of the control points P0, P1, P2, and P3 using this combination. So these three, or actually four polynomials that appear. 1 minus t cubed, 3 times 1 minus t squared t, 3 times t squared 1 minus t, and t cubed. So these coefficients here are polynomials in t. And we can rewrite this just by expressing it as a polynomial in t, okay, with coefficients that depend on the points. So just a rewrite of this after you expand it out and sort of collect similar powers of t. Now, the coefficients that are appearing here are, with respect to the points P0, P1, P2, P3, are the Bernstein basis polynomials, and they're often denoted B sub k3, in this case, in the cubic case. So B sub k3, when k goes from 0 to 1 to 2 to 3. And here is the Wikipedia entry. I don't know if you can read this. Maybe let me try to make it a little bit bigger. Okay, well, if you can just go to Bernstein polynomials and you can find it. And so here's the general formula. It's some binomial coefficient times a power of x times a power of 1 minus x. The same kind of thing that you see here. You have power of 1 minus t times a power of t times some binomial coefficient. So here the binomial coefficient is 1, 3, 3, 1. In fact, you see exactly these things here, exactly along this bottom row here. If you look at this bottom row, you see 1 minus x cubed, 3x, 1 minus x squared, that's essentially this one, 3x squared, 1 minus x, that's this one, and x cubed, that's this one. And here are graphs of these four functions. So this first one, okay, when x is 0, that's equal to 1. That's this red one. This next one, that's, I guess, this yellow one. This next one is, well, maybe these are, I can't read. This looks like the sort of, these are the degree 4 ones. So a 4th degree curve. This is one higher degree, but in any case, it's a similar kind of thing. If you plot these things, you get some nice curves that look a little bit like this. Now, this is all for degree 3, so you can do this for any degree. So we've seen here are the Bernstein basis polynomials of degree 2, okay? And actually, we also saw there they are of degree 1. Okay, so interesting. Mathematics naturally connected. And if we unravel this cubic case, just like we did before, then we are getting a curve of degree 3, because the highest power of t that occurs is the t cubed. So we can write what we get as a polynomial in t times another polynomial t. And the coefficients are just generalizations of what we've already done. And all of these coefficients can be encoded nicely in a little matrix like this. Okay? Constant terms, linear terms, quadratic terms, cubic terms. And over here are the control points, P0, P1, P2, P3. Okay? And this is this beautiful matrix here that connects the coordinates of the control points to the coefficients of the polynomials that you get once you've expanded everything out in t. And again, a natural question would be, what would happen if we tried to invert that? Does that thing invert? Happily, it does. Okay, so there's some interesting linear algebra that's appearing here. And if you think about this for a little while, here's the critical thing that, and I talk more at length of this in the algebraic calculus course, but there's really a single sort of big matrix, actually better a maxwell if you know what those are. But anyway, let's think of a matrix that's kind of going on. It's really a Pascal type of matrix. So this is a matrix that's like lower diagonal, got ones on the diagonal. And the rows here are just the usual rows of the Pascal triangle. 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, etc. Now, this thing goes on, okay? But if we sort of truncate it up to a certain level, like if we take this thing here, let me just grab that, copy it, okay? And let's say I take its inverse. Have a look what I get. I get exactly the same thing, except that now some signs have appeared. And where do the signs appear? The signs appear on these diagonals, sort of subdiagonals. The first subdiagonal, and then the third subdiagonal, and then the fifth subdiagonal, and so on. So there's a checkerboard pattern of minus signs. Now, this is a very beautiful situation because usually calculating inverses of matrices, especially big matrices, is painful. And there's not a direct relationship between the inverse of a matrix and the matrix. So this is a highly unusual, highly regular situation. Okay, and the fact that I'm just doing it here in the 5x5 case, it's completely general. You take any top left submatrix of this situation and take its inverse, you're going to get the corresponding submatrix over here. So in a sort of an ongoing sense, these two matrices or ongoing matrices are inverses of each other. That one's P, this one's Q, let's say, all right? Great. Okay, so then these matrices that we were obtaining, these change of basis matrices, that we went from the P's to the C's. Okay, you remember this one here? That was in the linear case, and this is the quadratic case, and this is the cubic case. These change of matrices you can then test are just what you get when you take this big matrix here and multiply it by, in this case, this 2x2 identity matrix. This one here is obtained by taking the same Q and multiplying it by this matrix 1, 2, 1. Again, Pascal kind of matrices, but now along the diagonal. This thing here, multiplying Q by 1, 3, 3, 1. Now I have to say, what? Are you allowed to multiply a 3x3 matrix with this ongoing matrix? Well, yes, you can if you've learned about maxils. Okay, so I talk about maxils in my Math Foundation series, somewhere probably in the 200s. Very important kind of generalization or larger scale view of matrix theory. Okay, but basically what you can think is you can just think about doing the following. You can just, in order to calculate this thing, you just truncate this Q and look at the top part of it. So let me just illustrate that. So if I take this thing here, there it is. That's the top part of Q, and I grab this matrix here and I put it in front of it. Let's see if it'll multiply these two things. Equals. You see, I am getting that 3 by 3 matrix there. Okay. So what that is then telling us is that there's a pattern to these matrices that we got. I mean, at first you might think, what's the pattern here? You know, what's the relation between this 3 by 3 one and this 2 by 2 one? Okay. Well, a nice way of stating it is that it's just it's all dependent on this single ongoing matrix Q. Okay, and we're basically taking top portions of this and multiplying them by these pleasant diagonal matrices, which just ultimately multiply, I guess, rows by Pascal binary coefficients. All right, so this allows us to conclude that this transformation between the P's and the C's, okay, that we've observed in these low-dimensional cases is really quite general and allows us to formulate this major theorem, which we might call the DCB parametrization theorem, which is that a polynomially parametrized curve, gamma, is a DCB curve, and a DCB curve is a polynomially parametrized curve. So these two things are the same. Whether you're starting with a curve, which is a pair of polynumbers, or whether you're starting with a DCB curve generated by control points, they are the same thing. Okay, and that's really the reason why the DCB curves are so important, because really you're getting just the polynomially parameterized curves, which are the most fundamental and simplest curves to deal with in calculus. So another way of saying this is that given a parameterization, the control points P0, P1, and P2 are determined. And given the control points, the polynumbers P and Q that define the curve are determined. In fact, what I've shown you is an exact linear algebra prescription from going from one of these things to the other. So this is the bridge from the algebraic geometric side, namely a polynomially parameterized curve, to a discrete object, which is really the DCB control points. So there's a lot in this lecture. If you are new to the algebraic calculus, you probably want to spend several hours going through what I've stated and said and verifying it yourself. Make some computations, convince yourself of it. If you're a member of the Wild Egg Math channel, I'm going to make available to you auxiliary things like the GeoGebra worksheet, so you can play around with that to get some physical sense of these DCB points, or you can generate it yourself because GeoGebra is freely available. Okay, so this is a great starting point. We're heading towards all kinds of interesting investigations about the geometry of these DCB curves, which I claim is really at the heart of calculus. And this first lecture is really critical that you understand, how we get control of the control points and the relationship with the actual polynumbers that generate a DCB curve.